Hello everyone, my name is Satish Sivashanmugam. I'm working as a senior cybersecurity engineer at American Express. Today I'm presenting my research titled Machine Learning Driven Threat Detection and Response Framework for Modern Cybersecurity Systems. So, this paper tackles one of the most impressive challenges in modern security operations. Building systems that can not only detect threats accurately but also explain their decisions and respond automatically. So, over the next several minutes, I'll walk you through the problem I'm solving and the methodology I designed, the models I have built, and the results I achieved. So, I hope this gives you a clear picture of how machine learning can bring meaningful improvements to cybersecurity defense systems. So, let me begin with the problem first. So, we are all living in an unprecedented expansion of digital infrastructure, right? Cloud computing, IoT devices, edge computing, and highly interconnected systems have collectively increased both the scale and the complexity of cyber threats. Traditional systems, primarily rule based or signature based detection, rely on predefined patterns of known attacks. So, while effective in stable environments, they fail against zero-day exploits or polymorphic malware and advanced persistent threats that constantly evolve. So, they generate excessive false positives that fatigue security analysts, and they cannot generalize to attack patterns that they have never seen before. So this created a clear gap in the field, a need for an intelligent adaptive framework that can learn from historical data, generalize to new threats, and operate at the speed and scale like a modern networks demand. So that is a problem my research addresses. To bridge that gap, I propose a three-component framework. The first component is Ansible machine learning for threat detection. Instead of relying on a single algorithm, I combine multiple models to improve both accuracy and robustness, a technique well established in the ML community. The second component is an automated response mechanism. Once a threat is detected, the system assign a severity level based on the model's confidence score and triggers predefined security actions such as logging the event, generating an alert, or isolating the affected node. This eliminates the need for manual triage in every case. The third component is explainable AI using a technique called LIME. I will explain more about the LIME in the upcoming slides. Security analysts cannot blindly trust a black box model. So LIME gives us local explanations for each prediction, showing which features drove the decision. This is critical for trust, compliance, and forensic investigation. Together, these three components create a framework that is accurate, actionable, and transparent. So the framework is evaluated on the CICADS 2017 dataset. Many of you might have already used that dataset. It stands for the Canadian Institute for Cybersecurity Intrusion Detection dataset from 2017. So this is one of the most widely cited benchmarked datasets in intrusion detection research. So it contains approximately 620K network flow records with 78 features per record. So these features include statistical measurements of each network flow, things like packet length, inter-arrival time, protocol type, flag counts, and traffic rate. The dataset covers a wide range of attack categories like the distributed denial of service, DOS variants like the Hulk and slow loris, brute force, botnet, FTP, and SSH, pattern attacks, web attacks, port scan, and infiltration alongside benign traffic. One important characteristic is significant class imbalance. Benign traffic accounts for over 483K samples, while some attack categories have far fewer instances. This imbalance is a real world reality, and how models handle it matters enormously in practice. Before training any model, I performed a data pre-processing and feature selection, two steps that are often underestimated but have a larger impact on the model quality. So during pre-processing, I first checked for missing values, then performed outlier detection, removing approximately 20,000 abnormal rows. I then removed duplicate records, bringing a final cleaned dataset of just over 590K records. For feature selection, I used a correlation based approach. I computed the absolute correlation matrix across all 78 features and eliminated any pair of features with their correlation above zero point 0.9. I retained only the most informative one from each highly correlated group. So this reduced the feature space from 78 down to 45 features. It cut the dimensionality by more than 40%. So the benefits are significant actually. So it resulted in lower computational costs, and then the reduced risk of overfitting. So and also improved model generalization as well. I also applied a robust scalar normalization, which uses the median and interquartile range rather than mean and standard deviation. So it made it more resilient to the outliers common in network traffic data. I trained and evaluated three models to establish a fair comparison. So the first is the random forest, a bagging ensemble that trains multiple decision trees on bootstrap samples and aggregates their votes. It is known for low variance and stable predictions. I configured it with 30 estimators and a max depth of 5 to prevent overfitting on the high dimensional feature set. So the second is the XGBoost, a sequential boosting algorithm. This builds the trees on one at a time, each correcting the errors of the previous one. So I used 30 estimators with a low learning rate of 0.05, shallow max depth of 2, and L1 and L2 regularization to control complexity. XGBoost is generally more sensitive to hyperparameters than random forest, but often achieves better precision on difficult classification tasks. So these two individual models serve as my baselines. So the third model, my main contribution builds on both. So the hybrid stacking model is the core innovation of my research. Stacking is a meta-learning technique where I use multiple base models, in this case random forest and XGBoost, and feed their output predictions into second level model called the meta learner. So here is why this works so well. Random forest and XGBoost have complementary strengths. Random forest reduces variance and provides stable predictions across a wide range of samples. XGBoost reduces bias by iteratively correcting misclassifications. When you stack them together, you get the benefit of both. So I chose the logistic regression as a meta learner. It is a very lightweight, interpretable, and it is also less prone to overfitting than more complex meta learners. So the logistic regression model learns the optimal weights to combine the probabilistic outputs from both base models. To avoid data leakage, I used cross validation to generate out of world predictions for training the meta learner. So this ensures the meta learner is trained on predictions it has never seen before, producing a more honest performance estimate. So the result is a model that is greater than the sum of its parts, achieving better classification stability across diverse and imbalanced attack categories. Now let me look at the results. So the hybrid RFXG boost stacking model achieved a 99.44% accuracy, 99.35% precision, 99.44% recall, and an FN score of 99.39%. So compare this to random forest at 98.63% accuracy and XGBoost at 98.01%. These are all like very strong results, but the hybrid model consistently outperforms both across all matrices. So looking at the confusion matrices, the hybrid model correctly classified over 48,669 samples and 12,469 DDoS samples with a very few misclassifications. It also showed improved balance between false positives and false negatives across minority attack classes. So from the ROC curves, the macro average AUC values are 0.956 for random forest, 0.952 for XGBoost, and 0.942 for the hybrid model. So while the macro average AUC of the hybrid appears slightly lower, the per class detection accuracy and the overall FN score tell a clearer story actually. So the hybrid model achieves the most balanced and reliable classification across all attack categories. The training time for the hybrid model is approximately 200 seconds expected, given the ensemble overhead, and but the testing time is under just 1 second only. So making it viable for production deployment. So one of the differentiating aspects of this framework is the integration of explainable AI using LIME, which actually stands for local interpretable model agnostic explanations. The challenge with the Ansible model is that they are just black boxes. A security analyst looking at a prediction of DDoS attack with a 99.8% confidence needs to know which features drove that conclusion before they can act on it or verify it. So Lime solves this problem by training a simple interpretable surrogate model, specifically a linear model, in the local neighborhood of a given prediction. So it perturbs the input features and observes how the prediction changes, identifying which features have the strongest influence. So in my framework, I used a Lime tabular explainer trained on the scaled dataset with the 45 selected feature names. For a sample prediction of attack class 0 with the 99.8% confidence, Lime identified the top 10 contributing features, including the backward packet length, total backward packet length minimum, flow bytes per second, forward packet length maximum, and FIN flag count. So positive weighted features pushed the prediction towards the identified class. So negative weighted ones are opposite. So this kind of explanation allows analysts to correlate model decisions like with the known attack signatures, validate the model's reasoning, and build operational trust in the system. So to conclude my research, I present a comprehensive ML-driven framework for cybersecurity threat detection that addresses three critical dimensions: detection accuracy, automated response, and model transparency. So the hybrid RG-XG boost stacking model outperforms individual models with the 99% accuracy across all key metrics. The automated response mechanisms maps detected threats to actionable security responses based on prediction confidence. And the line-based XAI module makes the model's decision interpretable and auditable. I do acknowledge limitations actually. So the stacking architecture adds computational overhead during training. The CICIDS 2017 dataset, while widely used, represent controlled experimental traffic and not live production networks. Class imbalance among minority attack categories remains a challenge actually. So, future directions include real-time deployment testing, advanced imbalance handling techniques such as SMOTE, or cost-sensitive training, and exploration of lightweight transformer-based architectures to improve scalability in dynamic network environments. So, thank you for your time and attention. I hope this presentation gave you a clear understanding of how Ansible machine learning, automated response, and explainable AI can be combined into a practical and effective cybersecurity framework. If you have any questions, please reach out to me at satish@gmail.com. Thank you so much.